Welcome to today's problem walkthrough. In this session, we'll dive into problem number 2126, Destroying Asteroids. We'll explore the problem, break it down step by step, and discuss potential approaches to solve it. Let's get started. In this problem, you're tasked with determining if a planet can destroy all the asteroids in its path. The planet has an initial mass, represented as a positive integer mass. You are also given an array of asteroids, where each element represents the mass of an asteroid. The rule is simple: the planet can destroy an asteroid if its current mass is greater than or equal to the asteroid's mass. When an asteroid is destroyed, the planet's mass increases by the mass of that asteroid. Your goal is to return true if it's possible to destroy all the asteroids in the array. Otherwise, you return false. The input constraints ensure that the planet's mass, the array length, and the asteroid masses all range between 1 and 100,000. The output is a Boolean value based on whether all asteroids can be destroyed or not. Let's take a look at a concrete example to better understand the problem. Suppose the planet starts with a mass of 10, and the array of asteroids is 3, 9, 19, 5, 21. Here's how the process unfolds. The planet first destroys the asteroid with mass 3, since 10 is greater than or equal to 3. Now, the planet's mass increases to 13. Next, it destroys the asteroid with mass 5, as 13 is greater than or equal to 5, and the new mass becomes 18. The asteroid with mass 9 is destroyed next, increasing the planet's mass to 27. Then, it destroys the asteroid with mass 19, which brings the mass to 46. Finally, it destroys the asteroid with mass 21, resulting in a final mass of 67. Since all asteroids are destroyed, the output for this example is true. Now consider another example where the planet starts with a mass of 5, and the array of asteroids is 4, 9, 23, 4. The planet begins by destroying the asteroid with mass 4, increasing its mass to 9. It then destroys the next asteroid, which also has a mass of 9, bringing the planet's mass to 18. However, when it encounters the asteroid with mass 23, the planet's mass is no longer sufficient to destroy it, as 18 is less than 23. At this point, the planet cannot proceed further, so the output is false. This example demonstrates how the planet's inability to destroy even one asteroid results in a failure to destroy the entire array. Here's a third example to illustrate an edge case. Suppose the planet's initial mass is just 1, and the asteroid array is 100, 200, 300. In this scenario, the planet encounters the first asteroid with a mass of 100. Since its mass of 1 is far less than the asteroid's mass, it cannot destroy it. Therefore, the process ends immediately, and the output is false. This example highlights how starting with a very small initial mass can make it impossible to destroy even the first asteroid, let alone the rest of the array. To summarize, the problem involves determining whether a planet can destroy all asteroids by sequentially increasing its mass as it destroys each asteroid. The constraints ensure a wide range of test cases, from very small to very large values. For instance, a planet with mass equals 1 and an asteroid array of 10 to the power of 5 cannot destroy the single large asteroid, so the output is false. On the other hand, a planet with an initial mass of 10⁵5 and multiple asteroids, each with a mass of 10⁵5, can destroy all asteroids one by one, resulting in an output of true. By carefully analyzing the initial conditions and the asteroid masses, you can determine the correct output for any given input. To solve the problem of destroying asteroids, let's first consider the brute force approach. The idea here is to evaluate all possible orders in which the asteroids can be destroyed. For each permutation of the asteroids, we check if the planet's current mass is sufficient to destroy each asteroid in that order. If the planet's mass is greater than or equal to the asteroid's mass, the asteroid is destroyed, and its mass gets added to the planet's mass. If any permutation allows the planet to destroy all asteroids, we return true, otherwise, we return false. However, this approach has a major drawback: generating all permutations has a time complexity of O(n), which grows factorially with the number of asteroids. This makes the brute force method computationally prohibitive, even for moderate input sizes. To address this inefficiency, we can use a greedy approach. By focusing on the order of destruction, we can make the process much more efficient. The key observation is that destroying smaller asteroids first maximizes the planet's growth rate. By sorting the asteroids in ascending order, the planet's mass increases as quickly as possible as we process each asteroid. If the planet's mass becomes insufficient at any point, we can immediately return false. Otherwise, if all asteroids are destroyed, we return true. This strategy avoids the exponential cost of the brute force method by eliminating unnecessary permutations. The greedy approach stands out for its efficiency. Sorting the asteroids in ascending order takes O(n) log n time, and iterating through the sorted list requires only O(n). This gives the greedy solution an overall time complexity of O(n) log n. Additionally, if sorting is performed in place, the space complexity is O(1), making it memory efficient. This approach is optimal for the problem because it eliminates redundant checks and ensures that we are always making the best possible decision at each step. While a dynamic programming solution could be considered, it introduces unnecessary complexity. In such an approach, we would track the state of whether a subset of asteroids can be destroyed with a given mass. However, the greedy method already guarantees the optimal solution without the overhead of maintaining a DP table. The time complexity for a dynamic programming solution would be O(n*m), where m is the sum of all asteroid masses, and the space complexity would also be O(n*m). Given that the greedy solution is both faster and more memory efficient, there's no practical reason to choose the dynamic programming approach. By leveraging the simplicity and correctness of the greedy strategy, we achieve an elegant and efficient solution to the problem. There are some key observations that make the greedy approach particularly effective. First, destroying smaller asteroids first ensures that the planet's mass grows as quickly as possible, maximizing its ability to destroy larger asteroids later. Second, sorting the asteroids allows us to process them sequentially in a single pass, eliminating the need for backtracking or exploring alternate orders. This simplicity is what makes the greedy approach not only optimal but also easy to implement. Importantly, the problem does not require us to track subsets or alternate orders of destruction, which is why more complex strategies like dynamic programming are unnecessary. Comparing the three approaches, the brute force method is infeasible due to factorial time complexity, while the dynamic programming approach is less efficient in both time and space compared to the greedy solution. The greedy method strikes the right balance between simplicity and efficiency, making it the best choice for solving this problem. In terms of complexity, the greedy approach achieves O(n) log n time due to sorting in O(1) space if sorting is done in place. This ensures that the solution is optimal and avoids unnecessary computational overhead, providing the most practical and effective strategy for destroying the asteroids. To solve the problem of destroying asteroids, the key lies in determining the order in which they should be destroyed based on the planet's initial mass. The planet can only destroy an asteroid if its current mass is greater than or equal to the asteroid's mass. Once an asteroid is destroyed, its mass is added to the planet's, allowing it to potentially handle larger asteroids. The challenge is to find an optimal order that allows the planet to destroy all the asteroids. The first step in this strategy involves sorting the asteroids by their mass. By starting with the smallest asteroids, we ensure that the planet's mass grows incrementally, minimizing the risk of encountering an asteroid that is too large to destroy. To achieve this, we use a sorting algorithm like quicksort or merge sort, which sorts the asteroid masses in ascending order. This sorting step has a time complexity of O(n** log n, where n is the number of asteroids. After sorting, we move on to iterating through the sorted asteroid list to determine if the planet can destroy each asteroid in sequence. During the iteration, we initialize a variable called planet_mass to represent the planet's starting mass. For each asteroid in the sorted array, we check if the planet's current mass is greater than or equal to the asteroid's mass. If the condition is met, the asteroid is destroyed, and its mass is added to the planet's mass, allowing it to grow further. However, if the planet's mass is insufficient to destroy a particular asteroid, we stop the process immediately, as the sequence is no longer feasible. This iterative approach ensures that smaller asteroids are handled first, which is crucial for incrementally growing the planet's mass. Once this loop is complete, we determine the result. If all asteroids have been destroyed successfully, we return true. Otherwise, if the process is halted due to an insufficient mass, we return false. The greedy strategy of always targeting the smallest asteroid first is what makes this approach effective. By sorting the asteroids initially, we simplify the decision-making process, and the fail-fast mechanism ensures computational efficiency by terminating early if destruction is impossible. The data structures used in this approach are minimal but effective. The asteroid masses are stored in an array, and sorting followed by a single traversal of this array is sufficient for the solution. Additionally, a single variable, planet_mass, keeps track of the planet's growing mass as asteroids are destroyed. From a complexity perspective, the most computationally expensive step is sorting the asteroid array, which takes O(n*log n). The subsequent iteration through the array is linear, with a complexity of O(n). Therefore, the overall time complexity of the algorithm is O(n*log n). Space complexity depends on the sorting algorithm used. For example, mergesort requires O(n) extra space, whereas quicksort can be performed in place, requiring minimal additional memory. A few edge cases must also be considered. If the asteroid array is empty, there are no asteroids to destroy, so the result is true. If the planet's initial mass is smaller than the smallest asteroid, the result is false immediately. Additionally, the algorithm should handle large values of mass without causing overflow errors, making the choice of data types critical. Finally, if all asteroids are destroyed successfully, we return true as the result. Let's now look at the pseudocode for this approach. We begin by taking the planet's initial mass and the array of asteroid masses as inputs. The first step is to sort the asteroid array in ascending order. Once sorted, we iterate through each asteroid in the array. For every asteroid, we check if the planet's current mass is greater than or equal to the asteroid's mass. If it is, the asteroid is destroyed, and its mass is added to the planet's mass. If the planet's mass is insufficient to destroy an asteroid, we immediately return false, as it's impossible to destroy all asteroids. If the loop completes successfully and all asteroids are destroyed, we return true. This pseudocode encapsulates the entire algorithm in a concise way, highlighting the core steps of sorting, iterating, and updating the planet's mass. The greedy strategy ensures that we make the optimal choice at each step, and the early termination condition improves efficiency when destruction is not feasible. This solution to LeetCode problem number 2126, destroying asteroids, is designed to determine whether a planet can destroy all asteroids in an optimal order. Here's a detailed explanation of the implementation. 1. Sorting the asteroids. The first step is to sort the array of asteroid masses in ascending order. This ensures that we attempt to destroy smaller asteroids first, maximizing the chances of survival. Smaller asteroids require less mass to destroy, and destroying them earlier allows the planet to grow in mass incrementally to handle larger asteroids later. 2. Iterating over the asteroids. The algorithm iterates through each asteroid in the sorted list. For each asteroid, it checks if the planet's current mass is sufficient to destroy the asteroid. 3. Condition check. If the planet's mass at any point is less than the mass of the current asteroid, the function immediately returns false. This indicates that it is impossible to destroy all asteroids. For updating planet mass, if the planet's mass is sufficient, the asteroid is destroyed. The asteroid's mass is added to the planet's mass, effectively increasing the planet's ability to handle larger asteroids in subsequent iterations. 5. Returning the result. If the loop completes without returning false, it means all asteroids have been successfully destroyed, and the function returns true. This algorithm is efficient, with a time complexity of O(n)log n, due to the sorting step, where n is the number of asteroids. The subsequent iteration through the sorted list is O(n), making the overall complexity O(n)log n. The space complexity is O(1), since the algorithm sorts the input array in place and uses no additional data structures. This approach is optimal and ensures that the solution is both correct and efficient for inputs within the given constraints. This is a full Java implementation for LeetCode problem number 2126, destroying asteroids. The logic mirrors the Python solution, utilizing sorting and a simple traversal to check if the planet's mass can absorb all asteroids in ascending order. Key differences include Java's use of primitive types, explicit array handling, and the arrays.sort method for sorting. The solution ensures clarity and adheres to Java conventions. To solve the problem, let's start with the first example where the planet's initial mass is 10 and the asteroids are 3, 9, 19, 5. The first step is to sort the asteroid array, which gives us 3, 5, 9, 19. Sorting helps us process the smallest asteroid first, making it easier to destroy asteroids sequentially. Now, we process the first asteroid, which has a mass of 3. Since the planet's mass, 10, is greater than or equal to 3, the asteroid can be destroyed. The mass of the asteroid is added to the planet, resulting in a new planet mass of 13. The remaining asteroids are 5, 9, 19. Next, we process the asteroid with a mass of 5. The planet's current mass is 13, which is sufficient to destroy the asteroid. The asteroid is destroyed, and its mass is added to the planet, increasing the planet's mass to 18. The remaining asteroids are now 9, 19. Moving forward, the next asteroid has a mass of 9. The planet, with a mass of 18, can destroy this asteroid as well. After adding the asteroid's mass to the planet, the new planet mass becomes 27, leaving only one asteroid, 19. Finally, the last asteroid has a mass of 19. The planet's mass, 27, is greater than 19, so the asteroid is destroyed. The planet's final mass becomes 46, and there are no more asteroids left. Since all asteroids are destroyed, the output is true. In the second example, the planet starts with a mass of 5 and the asteroids are 4, 9, 1. After sorting, the asteroids become 1, 4, 9. Now we process the first asteroid, which has a mass of 1. The planet's mass, 5, is sufficient to destroy the asteroid, so the asteroid is destroyed, and the planet's mass increases to 6. The remaining asteroids are 4, 9. The next asteroid to process has a mass of 4. With a planet mass of 6, the asteroid is destroyed, and its mass is added to the planet, resulting in a new planet mass of 10. The remaining asteroid is 9. Now, the final asteroid has a mass of 9. The planet's mass, 10, is greater than the asteroid's mass, so the asteroid is destroyed, and the planet's new mass becomes 19. There are no asteroids left, so all asteroids have been destroyed, and the output is true. In the third example, the planet's starting mass is 8, and the asteroids are 10, 3, 5. After sorting, the asteroids become 3, 5, 10. Now, we process the smallest asteroid, which has a mass of 3. The planet's mass, 8, is greater than 3, so the asteroid is destroyed. The planet's mass increases to 11, and the remaining asteroids are 5, 10. Next, we move to the asteroid with a mass of 5. The planet's current mass is 11, which is sufficient to destroy the asteroid. The asteroid is destroyed, and the planet's mass becomes 16. Finally, the last asteroid has a mass of 10. The planet's mass, 16, is greater than 10, so the asteroid is destroyed, and the planet's mass increases to 26. With no asteroids left, all asteroids have been destroyed, and the output is true. To understand the time complexity of the solution, let's break it down step by step. First, the list of asteroids is sorted in ascending order using Python's built-in sort function. Sorting an array of size n takes n*log n time. Once the list is sorted, the algorithm iterates through each asteroid exactly once, making this step an O(n) operation. During each iteration, there is a comparison to check if the planet's current mass is sufficient to destroy the asteroid. This comparison is an O(1) operation, and if the asteroid is destroyed, its mass is added to the planet's mass, which is also O(1). Since these constant time operations are performed once per asteroid, they contribute an additional O(n) to the overall time complexity. Now, combining these steps, the total time complexity arises from two main components: the sorting step, which is O(n*log n, and the iteration step, which is O(n). Since the sorting step dominates the overall time complexity, the final result is O(n*log n. Looking at space complexity, the input list asteroids is directly used, which requires O(n) space. Additionally, Python's sort function uses timsort, an in-place sorting algorithm. However, in the worst case, timsort may require O(n) additional space for temporary storage during sorting. Additionally, the algorithm does not rely on any other data structures or recursion. All operations, such as comparisons and mass updates, are performed in constant space, contributing O(1). When we combine all these factors, the total space complexity is determined to be O(n), dominated by the space required for sorting. Now, let's analyze the best, average, and worst cases. In the best case, if the asteroids are already sorted and the planet's mass is sufficient to destroy each asteroid, the sorting step is still unavoidable, leading to a time complexity of O(n*log n and a space complexity of O(n). For the average case, where asteroid sizes are randomly distributed, the same steps of sorting and iteration apply, resulting in the same complexities, O(n*log n for time and O(n) for space. Even in the worst case, where the planet's mass is insufficient to destroy one of the smaller asteroids early in the iteration, the sorting step still dominates, keeping the time complexity at O(n*log n, with space complexity unchanged as well. Comparing this optimized solution to a brute force approach offers a clear understanding of its efficiency. A naive brute force method would involve testing all possible destruction orders of the asteroids. This would require computing all permutations of the asteroid list, leading to a time complexity of O(n). Such an approach becomes computationally infeasible for larger input sizes. In contrast, the current solution optimizes the process by sorting the asteroids first. By encountering smaller asteroids earlier, which are easier to destroy, the problem is reduced to a simple linear traversal after sorting. This reduction in complexity, from O(n) to O(n*log n, makes the algorithm highly efficient and scalable, even when the input size reaches up to the constraints of n being as large as 10 to the power of 5. When tackling this problem, it's important to be aware of common mistakes that can lead to incorrect or inefficient solutions. One major issue is failing to account for all permutations in a brute force approach. For example, if you try to generate all possible orderings of the asteroid array manually without using a reliable method like itertools.permutations in Python or a backtracking algorithm, you might miss critical test cases. Additionally, edge cases are often overlooked, such as an empty asteroid array or when the starting power of the planet is too low to handle even the smallest asteroid. These scenarios can result in runtime errors, so it's essential to explicitly test for them in your code. Another common pitfall is not optimizing for time complexity. While brute force methods can help validate correctness, they quickly become infeasible for larger inputs, especially when the input size approaches the upper constraint of 10,000. Switching to more efficient strategies like sorting or greedy algorithms is necessary as input sizes grow. Lastly, avoid using floating point arithmetic unless specifically required. Integer operations are usually sufficient for comparing asteroid sizes and power levels, and using floating point numbers unnecessarily can lead to precision errors that affect the correctness of your solution. Misinterpreting the problem statement is another frequent mistake. Many assume the goal is to maximize the number of asteroids destroyed, rather than determining whether all asteroids can be destroyed. This misunderstanding can lead to incorrect implementations, so it's vital to pay close attention to the problem's objective. From an interview perspective, recognizing patterns is key. Problems like this often benefit from greedy strategies, where sorting the input and processing it sequentially simplifies decision-making. These patterns are common in resource management and sequential decision-making problems. While brute force approaches can be helpful for building an initial understanding, they are rarely practical for large inputs. It's a good idea to mention in an interview that you plan to optimize after validating correctness. Additionally, be proactive in communicating your assumptions. Clarify constraints, such as non-negative asteroid sizes or positive starting power, as this demonstrates thoroughness. Finally, show an awareness of time complexity. For example, explain that brute force has factorial complexity, O(n), but a sorting-based greedy solution reduces this to O(n)log n, making it far more efficient for larger inputs. This problem is part of a broader category of challenges that require sorting and greedy algorithms. For example, LeetCode 435, which deals with non-overlapping intervals, requires a similar greedy strategy to maximize the number of intervals without overlaps. LeetCode 1029, two-city scheduling, involves sorting and making greedy decisions to minimize costs. Another example is LeetCode 881, boats to save people, which uses sorting and a two-pointer approach to optimize resource usage. Similarly, LeetCode 452, minimum number of arrows to burst balloons, demonstrates how sorting and greedy algorithms can simplify complex decision-making. Beyond these related problems, you can also explore alternative approaches to solving the asteroid problem. A simple greedy approach involves sorting the asteroids by size, then destroying them in ascending order. This ensures the planet's power is used optimally, though the trade-off is that sorting requires n log n time. On the other hand, a dynamic programming approach could be used to track the planet's power after each asteroid, considering various orders. While DP is more flexible and can handle complex problem variations, it's typically slower than greedy methods for large inputs due to its higher computational overhead. Another useful technique is the two-pointer approach, which can be employed when the asteroids are sorted. In this method, two pointers are used to simulate the destruction process efficiently. One pointer might track the smallest asteroid that can currently be destroyed, while the other could manage the overall sequence. The trade-off here is that while this method is more memory efficient compared to dynamic programming, it requires careful implementation to ensure correctness. Missteps in managing the pointers can easily lead to logical errors, so precision is critical. Overall, this technique combines efficiency with simplicity, making it a strong option for solving the problem when the input is sorted. Great work! To wrap up, we reviewed the problem and discussed a key greedy approach that leverages sorting to solve it efficiently. Remember the importance of analyzing trade-offs and recognizing patterns like greedy algorithms for sequential decisions. Thanks for joining, and stay tuned for more problem-solving insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!